Just now we are going on. One of our another invited. Yes, just now we are going to our another invited session. One of the ENEFM Congress invited speaker, Professor Xiaojiang Wu from Shanghai, Jiao Tang University from China. The title is going to be Research Progress of 650 and 700 centigrade degree ultra supercritical coal-fired power generation technology in China.
Ladies and gentlemen, thank you very much for listening my presentation. The topic of my presentation is research work progress of 650 700 degrees C ultra supercritical coal-fired power generation technology in China. I'm Xiaojiang Wu from Shanghai Jiao University. This is the content of my presentation. Including background of research works, research progress and the main barriers, main conclusions, and the future perspectives. As we
We are sorry about the technical problem. 1 minute after, we are going to start Professor Wu's presentation. And also, I would like to remind that this virtual congress is recording. Just now, we are going on.
Ladies and gentlemen, thank you very much for listening my presentation. The topic of my presentation is research work progress of 650 700 degrees C ultra supercritical coal-fired power generation technology in China. I'm Xiaojiang Wu from Shanghai Jiao University. This is the content of my presentation, including background of research works, research progress and the main barriers, main conclusions, and the future perspectives. As we know, the thermal power generation efficiency increased with the increase of main steam parameters. According to the further development development of ultra-supercritical units, further improvement of parameters is still in inevitable development chain of ultra-supercritical power generation. When the temperature and the pressure of main steam exceeds 650 or 700 degrees C and 30 megapascal respectively, the efficiency of thermal power generation units with double reheat will be further improved. The first USC power generation unit is at Tong power plant with 32.4 megapascal, 454 degrees C in 1959 in America in the world. Until now, the first 630 degrees C USC power generation with double reheat will be operated in 2021 in China, Yangcheng project. In order to increase the power generation efficiency at around 50%, EU, America, Japan, and China have already begun to start their own research program respectively since 1998. The development stage of power generation technology in China has four stages. Stage 1: ultra-high pressure units from the former Soviet Union before 1980s. Introduced the supercritical unit from Europe and America from 1980s to 1990. Introduced the license system and developed supercritical, ultra-supercritical technology since 1990 to 2000 years, developing the advanced USC technologies with higher temperature and higher pressure since the 2000 year. Until the 2018, there are 105 USC power generation units in China, and the standard coal consumption was decreased continuously from the 283.3 gram per kilowatt hours to 256.2 gram per kilowatt hours for USC power generation in units in the last decade. The largest capacity of 1,350 megawatt USC double reheat units with different location arrangement of steam turbine in Anhui Pingshan project will be operated in 2020, and the design coal consumption is around 251 gram per kilowatt hours. In the future, it's planned to build 35 megapascal, 650 degrees C, 650 degrees C advanced ultra-supercritical power generation unit with double reheat. Due to the problems of the superalien materials, the construction of 700 degrees C advanced ultra-supercritical units will be postponed to 2000. The above figures show the thermal power generation process and their temperature and the enthalpy lines at different temperature levels. There is still room to further efficiency improvement in the power generation system to upgrade the temperature at 700 degrees C level, but there are lacks of theoretical and experimental support for 700 degrees C boiler and turbine design and operating experience, especially for the long period test of characteristics of nickel-based materials. There is still room for further efficiency improvement in power generation system by the optimization of the thermal system. The efficiency gap between the actual steam water cycle to ideal Carnot cycle is mainly composed by the process loss and the internal losses, such as pressure drop loss, blade sealing, etc. According to the principle of minimum entropy generation, The heat release from combustion flue gas and the heat absorption system of steam are coupled to form and further optimized to Rankine cycle to form new ultra-high parameter coal-fired power generation system. Is the status of research works on 700 degrees C USC boiler mantle materials for the four countries. In order to obtain the exactly mantle temperature and the precise heat transfer coefficient efficient and the 700 degrees C USC conditions, a 0.03 megawatts test facilities was designed and constructed to simulate the heat transfer characteristics of high-temperature heating surface in advanced USC boiler in Shanghai Jiao University. The main parameters of superheated steam is 38 megapascal and 700 degrees C. Operating conditions is shown as in the table. The experimental data processing is shown in the formula on the left. The heat transfer coefficient K was used to couple the heat transfer between the combustion side and the working fluid side based on the interface temperature of the heating surface. The coupling relationship between the hydrodynamics of working fluid side and the combustion of the fluid gas side was established and obtained the temperature distribution characteristics under 700 degrees C US conditions. The red figures is show the program calculation flow chart of coupling model. Transfer coefficient K was used to couple the heat transfer between the combustion side and the working fluid side. The calculation error deviation of combustion side in the furnace and the working fluid side in the tube are shown in the pictures above. In order to simplify the calculation process, we have made assumptions for calculation each side of combustion and the working fluid. The specific description as shown in the table below. In the combustion side, the flow gas in each gen is consistent and the flow field is uniform. The water wall surface around the furnace has the same boundary conditions. Combustion mainly occurs in the combustion gen. The combustion produced are concentrated near the actual triangle circle and then flow up with the gas flow directions, regardless of the flux reflex. In the working fluid side, the water wall tube receives radiation and convectional heat transfer in furnace, neglecting the actual heat conduction. Working condition of flue gas side in furnace doesn't change obviously with time. Each tube has the same mass flow rate and the same fluid characteristics on the cross sections. The flow resistance of each section is mainly concentrated in the inlet section and the pressure keeps uniform. Based on the experimental data and the heat transfer coefficient and the furnace and the different loads was calculated, and the actual heat transfer coefficient of furnace was extrapolated at 507 megawatt load. The coefficient is 325 and 575 watt per meter square degree C. At 662 megawatts, the coefficient is 325 and 525 watt per square meter per degree C at 970 megawatt load. The coefficient is 350 and 400 watt per meter square per degree C. Figure is shows the temperature distribution of water wall temperature along furnace height in combustion gen for both 700 degrees C and 600 degrees C USC conditions at different loads. And the left figure is show the temperature distribution of front wall and the back wall of water wall along the direction of furnace is at different elevations. As you can see, the peak value of water wall temperature appears in the main combustion gen. The highest water wall temperature in the furnace is around 619 degrees C, which is 75 degrees C higher than that and the 600 degrees C ultra supercritical condition. The distribution of water wall temperature along the furnace parameter direction is similar and both 600 degrees C and 700 degrees C ultra supercritical conditions. The temperature fluctuation and the 600 degrees C condition is 670 degrees C and 34 degrees C respectively at 34 meter and 40 and 54 meters. And the temperature fluctuation is 85 degrees C and 57 degrees C respectively and 700 degrees C condition. These pictures shows that the effect of the distance of flame offset and the working fluid rate deviation in tube on tube surface temperature. It can be seen from the figure that with the increase of distance of flame offset, the temperature of water wall, the fluctuation deviation of tube wall increased by 35 degrees C. The effect of flow rate deviation on the maximum wall temperature is significantly higher than that of flame offset. Above figures shows the relationship between the surface metal temperature of heating surface and the allowable temperature for metal materials and the different extreme conditions. As it can be seen, like there are some conditions where the tube temperature exceeds the allowable material temperature 550 degrees C due to the existence of conditions on water flow rate deviation and the flame offset. The higher elevation means the higher sensitivity of tube temperature of water flow rate deviation and the flame offset. Main conclusion. Construct a 700 degrees C ultra supercritical condition heat transfer test facility with coupling both combustion and the hydrodynamic process at steam parameters with 15 to 40 megapascal, 350 and 717 degrees C. Developed a combustion hydrodynamic coupling heat transfer model and the wall temperature variation law and the 700 degrees C ultra supercritical conditions has been obtained. Based on the experiment data and the calculation result, based on the developed coupling heat transfer model, the highest water wall temperature in the furnace is around 619 degrees C, which is higher 75 degrees C higher than that and 600 degrees C ultra supercritical conditions. There are some conditions where the tube temperature exceeds the allowable material temperature 550 degrees C due to the existence conditions on water fluid deviation and the flame oxide. Perspectives. In order to solve the key issues on thermal safety of high temperature components in boiler, the following research works need to do in the future. The experimental apparatus at 700 degrees C, the conditions which combined with combustion and hydrodynamics is needed for the basic testing date to conduct the heat transfer characteristics at 700 degrees C level. The coupled heat transfer simulation procedures of the combustion and hydrodynamics with temporal and spectral variables is essential to the advanced ultra-supercritical boiler design and operating. The long-term test verifications is imperative for the higher temperature surface with various candidate materials. The 650 degrees C ultra-supercritical technology based on austenitic steel may be a transition between the existing 600 degrees C ultra-supercritical technology and the advanced 700 degrees C ultra-supercritical technology. Here.
Yes, I want to thank to Professor Wu about his interesting and very nice presentation. Just now, we are going to